Hello everyone and welcome to this new session on land surveying, which is about resection calculations. So let's start. The aim of resection is to determine the coordinates of an unknown point x by taking total station measurements to the control stations A and B, for example, from the unknown point x. Okay, so the aim of resection again is to determine the coordinates of this unknown point from two known stations A and B. So you have two stations that you know their coordinates and you know their locations on the ground. And you have one station that you know its location on the ground, but you don't know its coordinates. And this is the aim of today's session, to let you know how to calculate the coordinates of this unknown station, x. Data required for resection calculations are the coordinates of two known survey stations, of course, A and B, for example. And you need to do some measurements using total station to measure angle x and the length of line XA, this one, and the length of line XB, this one. So these are measured values, and also you need to draw a sketch of the area, and this will help you to do correct calculations. Let's take a numerical example so that you can understand the calculations in a good way. So as I have just mentioned, we need some known values. These are the coordinates of known survey stations, A and B. In this case, we have the values here in this table. We have the coordinates of A, easting and northing, and the coordinates of station B. And you will need some measured values. You have to do some measurements using your total station. I would like to mention something very important before we start the solution, that you need to have a very good understanding of the whole circle bearings. These are explained in details in this video here. So there is a separate video that I explained in it the whole circle bearing and the sighting north in detail with numerical example. So please, if you haven't watched that yet, please do watch it before you proceed with this video, because it is essential that you understand what is the whole circle bearing, because we will use this term a lot in today's session. If you haven't watched it yet, please do watch it and then continue with this video. And for the measured values, these values, also I explained in details how to do these measurements using total station. There is a video called Measuring Horizontal Angles and Distances for explaining how to measure an angle using total station. In other words, how to get these values using total station. And now I will go through this very quickly just to remind you, but it is better to watch the whole video on measuring horizontal angles and distances so that you will have a perfect understanding before you proceed as well. You will get your total station and set up your total station over station X, and then you will sight station A. And then you will look at the screen of your total station, and then you will write down the horizontal angle value here. This is the first measurement. So in this case, the first measurement is 0 degrees, 10 minutes, 8 seconds. And this is called face left over A. And then you will turn your total station towards station B, and you will look at the screen of the total station and get the value of the horizontal angle from the screen and write it down here. This is the second measurement. It is called face left over B. The value in this case, 53 degrees, 56 minutes and 3 seconds. And now you will flip the telescope of the total station and rotate the total station horizontally and re-sight station B again. This is the third measurement, and you will look at the screen of the total station. You will write the horizontal angle value here. This is called face right over B. This is the third measurement. And now you will return the total station towards A. You will sight A, the same, look at the screen of the total station and write down the horizontal angle value here. This is called face right over A. This is the fourth measurement. After you have done these measurements, face left over A and B, face right over A and B, you need to calculate the final face left, which is the second measurement here minus the first measurement here. And then you need to calculate the final face right, which is the third measurement from here minus the fourth measurement from here, and you will get a value. these two values should be very close to each other, and now you will get the average of these two values of the face left and face right. And this is called a mean angle, and this is our aim, which is the horizontal angle x in our case, which is the face left, this value, plus the face right divided by 2, just the average. And then in this case we have 53 degrees 45 minutes and 52 seconds for angle x. So now we've got the value of angle x, and now, as I explained in the video that I mentioned, at some stage you need to press F2 function to measure the distance between x and A and x and B, and then you will record them here. This is distance XA and this is the distance XB. And these are the three numbers we need from this table. Okay, just I will get this number, which is the value of angle x. I will get this number, which is the length of XA, and I will get this one, the length of XB. These are the measured values that I will use for my resection calculations. So let's return here. These are the measured values using total station, and as I mentioned, we have known values. These are the coordinates of the survey stations A and B. And don't forget your aim. Your aim is to calculate the coordinates of station X, this one. This station, you know its location in the ground, but you don't know its coordinates, and you are going to calculate the coordinates. So guys, if you are wondering, why do I need a station like this that I know its location and I don't know its coordinates? For example, let's say that you have a project area somewhere here, for example. This is your project area. Let's say it is a big area, and you need to survey this area or to set out buildings or roads, whatever you like to do here. So if you have roads here, buildings, lakes, green spaces, okay, it's a big project, for example, but you don't have any control stations close to this project, okay? For example, let's say the closest stations are here. This is station, for example, let's call it A, and you have another station here, for example, B, and these two stations are too far from your project location. So because of that, it's good to set up here temporary benchmark, temporary survey station that is very close to your project so that you can use it to do all the work that you need. So in this case, what you are going to do is you are going, for example, to fix a nail in the ground here, or a wooden pick if you have a grassed area. So you fix something in the ground. So you know the location of this point. Okay, you can see it in front of you, but you don't know the coordinates, and the coordinates are very important to help you to set out or to detail the area. Okay, in this case, the resection is very useful to help you to calculate the coordinates of this temporary benchmark. Let's call it X, easting and northing of X, based on these two control stations. Okay, so these are benchmarks with known coordinates, with known locations, and you have the location here. You can set up your total station, do these measurements, measure the length of XB, this line, and the length of XA using total station, and you can measure angle X as well. And then you will do the procedure that you will learn now for the resection to calculate easting and north of this station. Once you have easting and northing, you can do all the work that you need for your project area based on this temporary benchmark. Okay, so this is the importance of this kind of calculations. I summarized the procedure for doing the resection calculations in 4 main stages. First, you need to calculate the whole circle bearing of AB and the whole circle bearing of BA. And then you are going to use the sine rule to calculate angles A and B. And then you need to calculate the whole circle bearing of AX and BX. And finally, you will apply some simple relations to calculate the easting and northing of X, and this is our aim. As you notice that I have used the term whole circle bearing a lot, so it is important to understand what is the whole circle bearing, how to calculate the whole circle bearing, everything related to whole circle bearing from this video here that I have just mentioned. And also there is an important note here in the third stage. You need to draw a clear sketch of your area, That means you need to draw the location of station B, station A, and your station X. Roughly, it is a sketch. It shouldn't be accurate, but the locations, the relative locations of these stations should be drawn so that you can do correct calculations in the third stage. So let's start with the first stage, which is calculating the whole circle bearing of AB and the whole circle bearing of BA. For calculating the whole circle bearing of AB and BA, as you know, first you need to calculate the change in easting and the change in northing. We have this table, of course, this is given to us. These are known values for the coordinates of two survey stations A and B. These are given here. So the change in easting delta E AB is easting of B minus easting of A. This is easting of B. This is easting of A. So the difference between them will give you the change in easting. And similarly, the change in northing, northing of B minus northing of A. This is northing of B here from the table. This is northing of A. Okay, now I have the values of delta E and delta N. Then I'm going to calculate the length of line AB, the length of this line here from here to here. Length of line AB. Using this relation, so the length of AB is the square root of delta E of AB squared plus delta N of AB squared. So delta A and delta N from here, we have just calculated them. Okay, so let's apply this. So this is delta E and this is delta N. So the square root of delta A squared, which is 268.159 squared plus 408.589 squared. So this is the distance after I calculated this, the distance between A and B, the length of line AB, which is 488.727 meters. And now I'm going to calculate the quadrant bearing, which is the inverse tangent of delta E divided by delta N. Let's apply. This is delta E, this is delta N, and here, of course, you need to use absolute values for delta E and delta N. So the quadrant bearing is in this case 33 degrees 16 minutes and 38 seconds. And the whole circle bearing of AB would be 360 for this case minus the quadrant bearing. The quadrant bearing, we have just calculated this in this step. So it would be 360 minus 33 degrees 16 minutes and 38 seconds. And the whole circle bearing of AB for this case is 326 degrees. It's a very big angle. 43 minutes and 22 seconds. So this is the whole circle bearing of line AB. And then we are going to calculate the whole circle bearing of BA, which is called the back whole circle bearing, which is the whole circle bearing of AB minus 180 degrees. And in this case, it would be 146 degrees, 43 minutes and 22 seconds. Okay, so this is the first stage, which is calculating the whole circle bearing of AB and the whole circle bearing of BA. If you are asking yourself now, what is delta E, what is delta N, what is the quadrant bearing, why the whole circle bearing is 360 minus quadrant bearing, if you are asking yourself these questions, if you don't understand what's going on here, please stop now and go and watch this video, which is about whole circle bearing, as I mentioned before, because it is very important to understand all of these terms. Okay, now we completed the first stage, which is calculating the whole circle bearing of AB and BA. Let's move to the next stage. The next stage, which is calculating angles A and B. This angle and this angle. You know that we have angle X from our measurements. This is one of the measured values. So from our measurements, we have these three numbers. Using total station, we've got angle X, we've got the length of XB, this line, and the length of XA, this line. And these are here, the length of XA, XB, and angle X. These are all measured values using total station. And the length of line AB that we will need here in this stage is calculated in the previous slide. This is the length of AB. We have calculated that to be 488.727 meters. So now let me remind you about the sine rule before we apply it for our resection calculations. This is from trigonometry, as you know, just to remind you about it. If you have a triangle, the length of AX, for example, this line, the length of this line divided by sine opposite angle, sine this angle, which is called B in this case. So the length of XA or AX, the length of this line, divided by the opposite angle, this one, should be equal to the length of XB, this line, divided by sine the opposite angle, which is A. So the length of XB divided by sine A. And this should be equal to the length of this line, AB, divided by sine the opposite angle, which is X in this case. So the length of AB divided by sine X. So this is sine rule from trigonometry. The length of AX divided by sine B should be equal to the length of XB divided by sine A should be equal to the length of AB divided by sine X. We are going to use this rule to calculate angle A and angle B. Angle X is known from the measurements. XA is known, the length of XB is known, the length of AB is known. So all the distances between these stations are known and the angle X is known. So now, for example, let's take this section of the relation, this one here, which says the length of XB, which is known, divided by sine A. A is unknown, and this is our aim to find angle A. Should be equal to the length of AB, which is known, divided by sine X, and sine X is known because X is known. So the only unknown here is angle A. So from here I can calculate the value of angle A. And similarly we can do this for angle B. Now let's do the calculations so that you will understand this in a better way. Let's start with angle B. This is sine rule. It says the length of AX divided by sine B should be equal to the length of AB divided by sine X. Okay? From here we can get sine B, which should be equal the length of AX divided by the length of AB times sine X. All of these values are known. I know AX, I know AB, I know sine X. Let's use the numbers. The length of AX is 593 meters, 0.011, divided by the length of AB, 488.727, times sine X. X is 53 degrees, 45 minutes, and 52 seconds. Okay, using inverse sine, you can get the value of angle B, which is in this case, I have calculated that to be 78 degrees, 9 minutes, and 15 seconds. So this is the value of angle B. Now let's calculate angle A. Using sine rule, the length of XB, now we will use, instead of XA here, we will use XB. This one, the length of XB divided by sine A should be equal to the length of AB divided by sine X. Always the length of any line divided by sine the angle opposite to it. This is to make it easier to you. And from here we can get sine A, which is the length of XB divided by the length of AB times sine X. We have all these values. We have the length of XB. This is from the measured values using total station. The length of AB, this is calculated in the previous slide, and this is measured angle X. And using the inverse sine, we can get the value of angle A. Now we have angle A as well. So now guys, we have all the angles of this triangle. We have angle X measured, and we have angles A and B calculated using sine rule. Yeah? Now at this stage we are going to check the accuracy of our measurements. As you know, the summation of the triangle angles should be 180 degrees in theory. So the summation of these three angles, X, A and B in theory should be 180 degrees. Now we are going to find the summation of our angles, and the difference between the summation of our angles and 180 degrees is the error that we made when we have done our measurements for angle X and distances XA and XB. Let's see in our case. This is an important check that you have to do. So the angle summation A plus B plus X is 180 degrees, 0 minutes and 1 second in our case. This is very accurate result. The difference between the theoretical summation, which is 180, and our summation is just 1 second, which is very accurate, and so it is okay, we can proceed with our calculations. However, if you have a big summation here, for example 181 or 182, etc., that means that you have done something wrong in your measurements and you need to double check your measurements and calculations, and if you still have the same answer, that means that your measurements are not accurate and you need to repeat your measurements. Okay? Now let's move to the next stage, which is calculating the whole circle bearing of AX and the whole circle bearing of BX. At this stage, it's very important to have a very nice and clear sketch for your area, for the locations of these survey stations, and based on your sketch you are going to determine the calculations, as you will see now. Before I start, I will get these 4 numbers in front of me because I need them. The whole circle bearing of AB and the whole circle bearing of BA from the first stage, and angles A and B from the previous slide, okay, the second stage. So I need these 4 numbers. I will let them be in front of me. The first thing that you need to do on your sketch now, you are going to draw all the whole circle bearings. The non-whole circle bearings, these are the whole circle bearings of AB and BA, and the unknown whole circle bearings that you need to calculate. These are the whole circle bearing of AX and the whole circle bearing of BX. So let me remind you quickly about the whole circle bearing. As you know, the whole circle bearing is an angle from north clockwise towards the measured side. So the whole circle bearing of AB, for example, to draw it here, as long as I started with letter A, that means I'm over A. So the whole circle bearing of AB, I am here. So it's an angle from north clockwise towards line AB. This is the whole circle bearing of AB. The whole circle bearing of BA, I started with letter B, that means I'm over B. I will start from here. So from north clockwise towards BA. So this is the whole circle bearing of BA. Whole circle bearing of AB and whole circle bearing of BA in a nice way. And now the whole circle bearing of AX, we'll apply the same definition. We started from A, that means we are here. We are over A here. Okay. Now the whole circle bearing of AX, this is line AX. This is X here and this is A here. Okay. From north, this is north. From north clockwise towards line AX. So it would be from here to here. So this is the whole circle bearing of AX from north to line AX. Now the whole circle bearing of BX, we started from B, we are over B, and this is X here, so this is the line in this case, BX. So from north, this is north to line BX, and this would be the whole circle bearing of BX. Okay? So as you know, at this stage our aim is to calculate the whole circle bearing of AX, this one, and the whole circle bearing of BX, this one. How to calculate the whole circle bearing of AX? Let's start with AX from this sketch. Let's look at the sketch and then keep in your mind that you know this value of angle A and you know this value of whole circle bearing of AB. How to calculate the whole circle bearing of AX? If you look here, guys, the whole circle bearing of AX, this one here, this one, this is the whole circle bearing of AX, is angle A, this one, minus this value. Let's call this value theta, for example. If I just know theta, I will say it is easy to find the whole circle bearing of AX. It is angle A minus theta. Okay, but what is the value of theta? Theta is, if you look here, this is theta, and this is, as you know, the whole circle bearing of AB here. This angle is the whole circle bearing of AB, this one. So theta would be, in this case, 360 full circle minus the whole circle bearing of AB. Okay, so this is the value of theta. Now to calculate the whole circle bearing of AX, which is our A, this angle, it would be the whole circle bearing of AX, angle A, minus theta, as we agreed. This is theta, 360 minus the whole circle bearing of AB from here. So let's calculate the value. Angle A, 48 degrees, 4 minutes and 54 seconds, minus 360 minus the whole circle bearing of AB, which is 326 degrees, 43 minutes, 22 seconds. And this is the whole circle bearing of AX value for this case. In this case, we have station B here, station A here, and station X in this location. And it would be, of course, different from triangle to triangle. Okay, so if X is here, the whole circle bearing of AX and BX would be completely different. But if you have a nice sketch, you would be able to calculate the whole circle bearing of AX and the whole circle bearing of BX easily. Now let's clean everything and let's have a look how to calculate the whole circle bearing of BX. This is the whole circle bearing of BX. So angle B is known. Look how easy is that. Angle B is known and the whole circle bearing of BA, this one, is known. It's very easy and straightforward now. To get this angle, this one, the whole circle bearing of BX, this one, which is this one, the same, okay? This angle is the whole circle bearing of BA minus angle B, this small angle here, angle B. So let's have a look at the calculations. The whole circle bearing of BX is whole circle bearing of BA minus angle B. And we know these values from here. Let's use the numbers. This is the whole circle bearing of BA minus angle B, which is 78 degrees, 9 minutes, 15 seconds, and then we can calculate the whole circle bearing of BX. Now we have calculated the whole circle bearing of AX and the whole circle bearing of BX, and these are very important for the next stage. So these are the whole circle bearings of AX and BX. So let's move to the next stage and the last one, which is calculating the coordinates of X. This is the last stage of our work. And this is the aim of our work, calculating easting and northing of X, this station here. Now to let you understand this stage, let's imagine that you have a coordinate system easting and northing, as you can see here, easting and northing coordinate system. My aim is to calculate easting and northing of this station X. Okay, I know easting and northing of B, I know easting and northing of A, and I need to calculate easting and northing of X. For example, now this is here easting of X, and this is northing of X. For example, now if we take station A, easting of A here, this is known, northing of A, this is known, of course. Now from here you can tell that easting of X is easting of A plus this distance between them, which is called delta E between A and X. Okay, so now easting of X is easting of A, which is known, plus delta E, the change in easting between A and X, this distance. And this is what we are going to calculate now. And in a similar way, northing of X, this one here, northing of X, is northing of A, which is known, plus the change in northing between them. This is the change in northing between A and X. Okay, this will give us northing of X. So this is if we use station A. Now, we can repeat the same thing, but based on station B. Now, from station A, we can calculate easting of X and northing of X. Now we can calculate the coordinates of x as well using station B, because we know that this is easting of B, it's known, and this is northing of B, known as well. So in this case, easting of x would be easting of B, which is known, plus the change in easting between B and x, which is this distance from here to here. And this is what we are going to calculate now. This is called delta A bx. And for northing of x, this one, it would be northing of B plus this distance from here to here, which is delta n between B and x, this distance here. Now by doing that, we can calculate the coordinates of x twice from station A and from station B, and then the final coordinates of x would be the average values, as you will see now. Now let's go to the solution. Let's calculate first the change in easting between A and x, which is the length of AX. This is known, measured, guys, don't forget it. This is the length of AX times sine whole circle bearing of AX. The whole circle bearing of AX is being calculated in the third stage in the previous slide, and this is the value. Whole circle bearing of AX is 14 degrees 48 minutes and 16 seconds, and I calculated this, it's 151.527 meters. This is the change in easting between A and X, which is this distance from here to here. This is the change in easting between A and X. Okay. Now the change in northing between A and X, similarly we have the length of AX times cosine whole circle bearing of AX, and we will have 573.325 meters. This is the change in northing between A and X, which is the distance. This is northing of A. This is the change in northing between A and X. This one, delta N between A and X. The coordinates of X, as I have just mentioned, is the easting of A plus delta E between A and X, which is this number here. So now easting of X is easting of A plus delta E between A and X. Delta E between A and X is being calculated here. And the coordinates of A and B, as you know, they are being given in the table. In the beginning of this session, you have table for coordinates of A and B. You will need it now. So if you have easting of A plus the delta E between A and X, you will have the answer 9,321.427. This is easting of X from station A. Now let's calculate northing of X from station A very similarly. So northing of X from A, northing of A plus delta N between A and X, which is this number here. This is delta N between A and X. And you will have the answer 5,819.215 in this case. So now we have calculated the coordinates of X from station A. We will repeat this from station B. Delta E between B and X, the same relation, but instead of AX we will use BX. The length of BX, this is the length of BX, measured value, times sine whole circle bearing of BX. The whole circle bearing of BX is being calculated at the previous stage, and this is the answer, 419.685 meters. Now delta M between B and X, the length of BX times cosine whole circle bearing of BX, which is 164.738. And now easting of X from B is easting of B plus delta E of BX. This is delta E between B and X. Okay, delta E of BX, this one. Now northing of X from B is northing of B plus delta N between B and X. This is delta N between B and X. Just calculate these numbers very easily. And now you need to have a look at the results and then to take the average. So if you look at the easting of X from station A and easting of X from station B, you will see these are very close numbers. The difference between them is just 1 millimeter. Here we have 9,321.427. Here we have 9,321.426. So the difference between them is 1 millimeter. So we need to take the average and round to a millimeter accuracy. And if you look at the northing here, of x from A and northing of x from B. The difference between them is 2 millimeters. Here we have 217, here we have 215, so the difference is 2 millimeters. So again, now here we have to take the average. So the final coordinates of x are the average values, and we have these are the numerical values, the average of the easting and northing from station A and station B. Now by doing that, guys, we have calculated the coordinates of the unknown station. It is known on the ground but unknown in terms of coordinates. We have calculated now these coordinates using the resection procedure from two known stations A and B after doing total station measurements for this angle and this distance and this distance. And it is good to mention that at this stage you can judge your numbers as well. Always you need to judge your numbers and your work. So for example, when you are taking the average of the easting or the northing, if these two numbers, the easting of x from A and the easting of x from B, are far from each other, that means that you have done something wrong, measurements or calculations. Okay, you need to double check your work. So these should be very close because these are the coordinates for the same station. So they should be very, very close numbers. So I hope that was useful to you guys, and now you have a good understanding about doing all the calculations for the resection. If you need to calculate the coordinates of any unknown station that's important for your project and you know two stations close to it, you can now use the resection calculations for calculating the coordinates of the unknown station. Keep in your mind, to do the calculations you need at least 2 control stations. Of course, if you have 3, if you have 4, if you have 5, you can apply the same procedure. Yeah, but at least you need 2 control stations around you to apply the resection calculations. And also you need to do some measurements using total station for measuring the horizontal angle and 2 distances. And then to apply all the calculations that I explained in detail so that you will calculate the coordinates of the station X. Now, after you calculate this station, you can use it now as a benchmark or temporary benchmark, do any detailing work to survey an area or to set out a point, a building, a road, etc. Okay, I hope that was useful to you. Thank you very much for listening and take care. Bye now.